Well, most oxygen, again, is oxygen-16, the lighter isotope. 8 protons, 8 neutrons. But a little bit of it, about 0.2%, is the heavier oxygen-18. Again, 8 protons, because it's still oxygen, but in this case 10 neutrons to give it a total of 18 nucleons in its nucleus. These things are basically similar chemically, but again, they're different physically, and the oxygen-18 is heavier. And that means when water containing oxygen-16 is near the surface and is warmed, the oxygen-16 containing water evaporates preferentially because it's lighter. It's more likely to go flying out into the air than the heavier isotope. So what that already means is that oxygen-18 is depleted in the water that goes into the atmosphere. Atmospheric water vapor is somewhat depleted in oxygen-18. Why? Because the oxygen-18 preferentially remained behind when the water evaporated because its nuclei are heavier. So the water that's in the vapor in the atmosphere is depleted. It has less oxygen-18 than the natural abundance of oxygen-18. Now, what else happens? Well, water typically evaporates in the tropical regions where it's warmest, and it's transported into the temperate zone and into the Arctic zone by the motions of air that is one of the major conveyors of energy from the tropics to the poles. If we didn't have that conveyance, by the way, the poles would be a lot cooler relative to the equator than they are, but there's a transport of energy associated with the transport of heat and of evaporated water from the equatorial regions. However, in the process of going from the equator toward the poles, the oxygen-18 containing water, being heavier, tends to precipitate out more readily. And so first you evaporate water and it tends to be depleted in oxygen-18, and then as the water moves poleward, it gets further depleted. And how much depleted it gets, you can see, depends somewhat on the temperature. The cooler it is, for example, the more the oxygen-18 will precipitate out, and that leaves Arctic and Antarctic precipitation even further depleted in oxygen-18. And the cooler the climate, the sooner the oxygen-18 is gone, and so the more depleted is the precipitation that eventually falls in the Arctic. And that precipitation falls typically as snow. It eventually is compressed into the ice that makes up the ice sheets, and it preserves, as I said, either an individual yearly layering or in some cases just a smeared out layering that allows us approximately to date it. But if we go in and core that ice, pull out an ice core, we then have a datable, sometimes datable by year, sometimes datable by rough era, record of the temperature at the time that precipitation fell. Similar technique works the same way with the hydrogen isotopes, because again there's water that contains H1, and then about 1 every 6,500 waters contains an H2, a deuterium atom. So either oxygen isotopes or hydrogen isotopes can be used to date particularly ice cores. And of course they tell us something about conditions when that ice fell. And unlike the global average temperature that I talked about in the first lecture, they tell us about conditions at particular places, in Antarctica, in the Greenland ice sheet, or whatever. But we can infer from those something more general about the temperatures on the Earth. So what do we do with these different proxies, the tree rings, the coral reefs, the isotope ratios, and so on? Well, we put some of them together and make multi-proxy studies that take a lot of these proxies into account and do a detailed statistical analysis and try to reconstruct temperatures back into the past. And the rest of this lecture I'm going to spend primarily looking at some of those reconstructions of temperature. I'm not going to call them measurements because we haven't actually measured temperature. We've attempted to reconstruct temperatures based on these proxies and our well-founded scientific understandings of how these proxies reflect climatic conditions, including temperature, at the times that the tree rings were formed or the precipitation fell or whatever. The first set of proxy studies I want to talk about are studies that push us back roughly 1,000 years. And what these proxies suggest, what these proxy studies suggest, is that Earth's climate, to get to the bottom line quickly, is that Earth's climate at present, in the past few decades, has shown a warming that is unprecedented on the 1,000-year timescale. And I want to show you a graph here, or actually I want to show you a lot of graphs here. There are actually 11 graphs I want to show you. And these graphs represent 10 different reconstructions of the climate of roughly the past 1,000 years. So every wiggly line you see is a different scientist or group of scientists a different study of what the temperature probably looked like on Earth back over the last roughly 1,000 years. I said there were 11 lines. There's only 10 of those wiggly lines. There's a thick line that occupies only the rightmost portion of the graph and extends highest right at the rightmost edge. And that's the same instrumental temperature record that I showed you and talked about in Lecture 1. Now it's been crammed into this very short piece of the overall 1,000-year graph, and so you see that rise in the early 20th century, that fall in the mid-20th century, slight fall, it's exaggerated here, and then you see that very steep rise at the end of the 20th century, and you see all these wiggly proxy studies. They are not measurements of temperature, but reconstruction of temperature, and they all show roughly the same thing. There's some variation, and you can argue about that and talk about that and who's right and who's not right, but they all show basically a slight downward trend over roughly the first 900 years of the millennium, and then a fairly steep rise at the end. If you had to summarize that in one quick sentence, that's how you would describe the graphs. If you were a climatologist, you might want to go into more detail and talk in more detail about what's going on there. But the basic big picture is, over the last 1,000 years, there's been a very gradual decline in temperature, followed by a sharp upturn at the end of that period in roughly the 20th century, late 19th through 20th century. So on that basis, we can say that the temperature rise we've seen in the last few decades has been unprecedented on timescales of at least 1,000 years. Now, how good are these reconstructions? Well, that's a little hard to know. One has to assess them. One has to look at the statistical methodology used. But again, we're looking at 10 different studies. 10 different studies, 10 independent studies that all point to basically the same thing. The U.S. National Academy of Sciences did a study of these 10 studies and concluded that at least for the last 400 years we can have considerable confidence in these studies, and going further back the uncertainties get bigger, but the general trends are still basically the right thing. So these are not the final word on what temperatures have been doing on this planet over the past 1,000 years, but they almost certainly give us a pretty good picture of the overall big picture. And the overall big picture conclusion is that the temperature rise of recent decades, since about 1960s or 1970, has been unprecedented, at least on a 1,000-year time scale. So that's the beginning of the answer to the question I started this lecture with. How is the temperature rise we looked at in Lecture 1, augmented by these fingerprints, is that unusual in the history of the Earth's climate? And over 1,000 years, it looks like it probably is unusual. What happens if we go back further? Well, we can go back a lot further using ice cores from either Greenland or Antarctica, and there are a number of studies doing these. I'm going to show you some results from drilling at the Vostok station in Antarctica. It's a Russian site, and that climate record has been available for quite a few years. There's a newer study that goes back almost 1 million years. The Vostok study goes back about 500,000 years. There's a newer one now, goes back almost 1 million years by a European group. And I'm going to show you the results from the Russian Vostok area study. And here is a picture. This graph is showing a picture of the climate of the past 420,000 years. So you're seeing on the horizontal axis thousands of years before present, with the present at the right, 0 years before the present, going back to 400 and something thousand years. You're seeing temperature deviations on the vertical axis. These are measured in degrees Celsius from the present day temperature. You'll see immediately that there is a pattern to this picture. There's a pattern of relatively short, 10 to 20,000 years in duration, warmish spells when the temperature is at or about the present day temperature. Again, the present day temperature on this graph is 0. It's just arbitrarily chosen to measure deviations from the present day temperature. So if you look at 0, 0 represents the present day temperature. So some of those spikes go a little bit above the present day temperature by a few degrees, but most of the time is spent in a much lower temperature state. You'll also notice that we rise rather quickly into those warm spells, and then we fall rather slowly into the cool spells, and we rise again. And the time period between these warm spells is about 100,000 years roughly. So for the past roughly 500,000 years, this pattern doesn't go back unchanged like this too much longer, but for roughly the past 500,000 years, the Earth has been in a cyclic climate pattern in which the temperature has mostly been in a fairly low temperature state, and then it's risen for 10,000 years or so to a warmer state, stayed that state for a fairly short time, and then dropped down again, and again with a roughly 100,000 year periodicity. Now let's take a look at a close-up version of that. These cool periods are ice ages. The warm periods are called interglacials. And I want to focus now on the most recent cycle from the last warm period before the one we're in now and the ice age in between. So here's the most recent cycle. It's the same data, same temperature deviation from the present in degrees Celsius. The cool period is the ice age. About 120,000 years ago, I said the periodicity was about 100,000 years. About 120,000 years ago, there was a warm spell. We're now in another warm spell. We're not quite the warmest time in that warm spell, at least not yet. But there we are. And a number that I would like you to walk away from this course with is roughly the difference in temperature between that warm spell that we're in now, or one of these typical warm spells, and the temperature sort of typical of the ice age. So what is that difference? Well, you can argue, is it 10 degrees? Is it 4 degrees? It's not 1 degree. It's a lot bigger than 1 degree. It's not 100 degrees. It's not 20 degrees. It's, I would call it 6 degrees. You could call it 8 degrees. I'm sort of getting it typical here. But roughly 6 degrees Celsius separates the present climate from that of the ice ages when North America, all of Canada basically, and northern United States had a mile or two of ice sitting on top of them. When I said in the first lecture a few degrees can make a big difference, I meant it. A few degrees in the global average temperature can be the difference. 6 degrees in the global average temperature can be the difference between the present conditions and an ice age when there was 2 miles of ice atop Montreal, for example, or northern Vermont, or whatever. That's a significant difference. And so when you hear people talking about climate change of a few degrees, global average climate change of a few degrees is climatologically extremely significant. Now, what causes this change in Earth's temperature, this cyclic change? We don't understand all the details yet. But what we do understand is that this temperature change is not caused by any one particular factor. It's probably triggered by astronomical factors related to Earth's orbit. And those astronomical factors are probably things like the tilt of the Earth's orbit, the variation in the ellipticity of the orbit, how elliptical is the orbit, the changes in the tilt of the axis as the Earth goes around in its orbit change how much of the time is spent in winter versus summer. And all these things trigger very subtle changes. And what we believe then happens is that those subtle changes cause feedback effects in the Earth's climate system, feedback effects that I'll talk about a lot more when we deal with climate models. And we will see just exactly what we think causes these effects. And I'll say a little bit more about that in subsequent lectures and look in more detail at those orbital effects that we think cause this to be triggered. But again, these orbital effects are subtle. They are very small effects. Then they trigger changes within the climate system that rapidly build up the temperature into one of these warm spells. And then gradually, as the orbital parameters change slightly, we gradually drift back down into that low temperature state we call the ice age. So don't think of this as a clear indication that there is some dramatic effect causing the temperature change. No, there's some subtle effect that causes the beginnings of a temperature change. That temperature change then leapfrogs through various feedback effects in the Earth's climate, and away we go.